There are two vectors here. One is OA, already drawn out for you, and there is another vector M. Okay, the vector M is drawn horizontally towards the right hand side there. Let's draw in the following position vectors. So if I want to draw in OR1, where is that located on the diagram? OR1 is OA plus 1 time of M. So we will take the M vector and we continue towards the right hand side of the point A. And this reaches for me a point called R1. When we add vectors, we then move this towards here so that we get the R1 vector. Okay, so this blue line is parallel to this M as well. If I continue to vary the value beside the M, okay, I want to make the observation of what will happen. If I continue to add 3M, then what happens is we continue to go to the right side, but 3 times of that value M to reach this point called R2. And this can be further continued. When I want this point OR3, there is a -2 in the coefficient. Minus sign, as you should know by now, means you go in the backwards direction. So I move like 2 steps of M to reach this point called R3. So can we observe? Actually, what will happen if I keep trying to vary the coefficient that appears beside my M? I go from 1, 3 to -2. What we are obtaining is actually we are getting different position vectors of OR that will lie on a line. And where is that line that we have? I'm going to draw it out. So you are going to see that because you're only moving right or left, everything you get is going to lie on this red color line that I'm going to draw out. Okay, this is that line that we are looking at. As long as you vary the coefficient beside M, anything that you get now is actually a point that lies on this line. So this line, we also define it properly. This is line L. We will say that this line L will pass through my point A. It passes through this point A. And we want to know, the other thing is like gradient. Think of it like gradient. Which vector is it parallel to? My line is parallel to vector M. So we write in here it's parallel to your vector M. There are names given for these two things. So for a line, we call OA as a position vector of the line, okay, or a point on a line is the same. And M, in particular, we call this a direction vector. So direction vector just means a vector that is parallel to the line. So let me focus back on here first so that we can relate nicely. This 3, the only difference is the coefficient beside M. So what we would want to know is if I have any point R that is lying on the line, how do I expect the equation to be written out? If I want to write down what is OR, based on what we have seen here, we know that we only need to vary the coefficient, which means if I change the coefficient, we get to either right side or left side on this line. So any line or any point on the line will look like it's OA plus a certain multiple of M, lambda M, where lambda can be any real number. So we write lambda belongs to R. This is how we can present the equation of a point on a line. And it is exactly this that we will write in for the equation of a line. When we talk about equation of a line, it is effectively trying to write down position vectors of points on the line. Okay, this phrase of equation of a line is the same as position vectors of points on a line. So we will write in the same thing Instead of OR, usually when we write a line, we first start with the name. So L is the name of my line. Let me label also name of line. It's called L. And left-hand side, instead of OR, we will say it's R equals, but R represents OR. It's the same thing. Then we can write in something like A plus lambda M. Lambda, any real number, exactly the same as what I have above. This is how the equation of a line looks like, but let me label further. Whenever we say R, it's like what we have seen above. This is position vector of any point. This A is a fixed point on L. And M is called the direction vector. So when we write out the equation of lines later on, every line will take on this same type of structure. Always position plus lambda direction vector.